Okay, so let's keep going on to the second page. So that was an arithmetic sequence because it was formed through adding or subtracting. A geometric sequence is what we call one that is formed through multiplication or division. So for example, 3, 6, 12, 24 is an example of a geometric sequence because to get from one term to the next, we are multiplying by 2. So let's try to use a similar structure and see if we could find T50 in this case. Again, T5 is easy to find. I just take the fourth term and multiply it by 2. But to get further up, we're going to want to make an explicit formula. So let's start by just representing our pattern in a similar way. T1 is equal to 3. T2 is equal to 6, so I'm going to say that that's 3 times 2. T3, 3 times 2 times 2. T4 is equal to 3 times 2 times 2 times 2. So you'll notice once again, the number of 2's in this case is 1 less than the term number. So T4 is 3 times 2 to the 3. T3 is 3 times 2 to the 2. If you're thinking this feels sort of familiar, this is very similar to what we did in our exponential unit when we were sort of developing that formula. T50 in this case is going to be 3 times 2 to the power of, again, 1 less, so 49. And we don't need to actually calculate this. We should just leave this as 3 times 2 to the 49 because it's going to be a number that's too big to write accurately anyway. So we can also generalize with the formula. We're going to use A to represent the first term once again, but for geometric sequences, we're going to use R instead of D because R represents the value of the common ratio, whereas in an arithmetic sequence, we use D because it's a common difference. So T4, for example, is A times R times R times R. T50 is A times R to the power of 49. So Tn is A times R to the power of n minus 1. And there we go. That is our second formula. And I'm going to write these down again so that you have easy access for the next page. So we've developed 2 formulas so far. We have the arithmetic sequence, which is that Tn is equal to A plus n minus 1 times D. And we have the geometric sequence, which is that Tn is equal to A times R to the power of n minus 1. And so now we are going to use these formulas to then write an explicit formula for each of the following sequences. And once again, if you'd like to pause the video and try these on your own, I highly recommend that. Okay, I'm going to walk you through my answers now. The first one's actually probably the trickiest one, but if you can see what we're doing here is we're just dividing by 3. And dividing by 3 is the same thing as multiplying by 1/3, which is probably how I'm going to approach this. So this is geometric. So for a geometric sequence, Tn is equal to A times R to the power of n minus 1. In this case, my first term, A, is 10. The amount I'm multiplying by every time is 1/3 to the power of n minus 1. Easy peasy. The second one is arithmetic. I'm subtracting 1 every time. So Tn is going to be equal to A plus n minus 1 times D. So A in this case is 100 plus n minus 1 times D, and D in this case is negative 1. The next two look similar, but the first one is arithmetic. I'm adding 7 every time. The second one is geometric. I'm multiplying by 2 each time. And so we'll just make sure to represent those correctly. So the first one is arithmetic, adding 7, also starting at 7. So n minus 1 times D. So the first term is 7, and D is also 7. And the second one is geometric. And in this case, I'm multiplying times 2 each time. So 7 times 2 to the power of n minus 1. Don't get caught up in this and think that you can make this 14 you have to follow order of operation. So you have to raise 2 to the power of n minus 1 before you can multiply it by 7. So just leave it in that form. Okay, let's keep going. We can also work backwards to solve for other variables. So in this case, the question is how many terms are in the sequence 749 all the way up to this giant number in the 40 millions. So in this case, we actually know Tn. This is the last term or the nth term in the sequence. When I say how many terms, I'm asking you to solve for n. And this is geometric. We're multiplying by 7 every time. So I'm going to write down my geometric formula. Now, if you feel like you've got the algebra skills to tackle this, I suggest pausing the video and giving it a try. I'll walk you through it now. So in this case, I know the value of Tn. I can sub it in here. Starting at 7, I'm multiplying by 7 each time, and I'm raising that to the power of n minus 1. And now to solve this, the next step is going to be to divide both sides by 7. I'm actually going to do this on a calculator. Should I have done this in advance? Maybe. Okay, when I divide both sides by 7, I get 5,764,801 is equal to 7 to the power of n minus 1. And now we're solving for an exponent, so I hope you find this exciting. We get to use logarithms. It's probably the best and easy way of doing this. So this is going to be log 5,764,801 base 7 is equal to n minus 1. You can go ahead and pop that in your own calculator. If you've forgotten, the way that you can put this into your calculator is by doing log of the first number divided by log of the base. And when you do that, you get that n minus 1 is equal to 8, and therefore that n is equal to 9. So we can say, therefore, there are 9 terms in the sequence. Okay, let's try another one with a little bit of algebra. So in an arithmetic sequence where T6 equals 15 and T18 equals 160, determine the values of A and D. So in this particular case, I've told you it's an arithmetic sequence. So I'm going to start by writing my formula down. A plus n minus 1 times D. And of course, if you'd like to tackle this one on your own, once again, please feel free to pause the video. There are more examples like this in the homework for you to try too. So in this case, I know T6 is 15. So I know that when n is equal to 6, Tn is equal to 15. So I'll go ahead and sub that in. I don't know the value of A and I don't know the value of D. So this is giving me the formula 15 is equal to A plus 5D. Let's call this equation 1. And for equation 2, T18 is 160. So that'll be A plus 17D. Where I'm doing my n minus 1 of 18 minus 1 to give me that 17. And now, this might look familiar. We have 2 equations and 2 unknowns. Lots of ways we can solve this, but probably you're most comfortable with substitution or elimination. I'm going to use elimination. You do what you want. I'm going to take equation 2 and subtract equation 1. I think that's probably the easiest way for me to do it. So if you've forgotten, you write the equations on top of each other. And in this case, I'm just going to subtract. So 160 subtract 15 is 145. A subtract A disappears. That's the eliminating part. And this is equal to 12D. And that means that D is equal to 145 over 12. And actually, this does not reduce, funnily enough, because I know that 145 is 29 times 5, and those are both prime numbers, and 12 is 2 times 2 times 3 when I reduce it to primes, and nothing cancels in there. So 145 over 12 is the best we can actually do. Let's keep it as a fraction. And now solve for A. So I'm going to sub D into equation 1 to solve for A. So 15 is equal to A plus 5 times D. Don't let the fractions intimidate you. We're just going to solve this by getting common denominators on both sides. So the left side is going to be 180 over 12. Subtract whatever this is. When I simplify this, 725 over 12 is equal to A. And this is going to give me an answer that A is equal to negative 545 over 12. Okay, so the answers are a little gross, but the concept, I think, is the same kind of thing. We're just setting up the formulas, and then we're doing a little bit of algebra to solve for the unknown variables here. Okay, just a little bit further to go. Now, there is a famous story about sequences, which makes references to someone named Carl Friedrich Gauss, if you've ever heard of the Gauss math contest. Gauss is very famous in Germany. Apparently, he's actually on some German money for being a mathematician. But in this story, when Gauss was a child, his teacher was trying to keep his class busy. I don't know, she wanted to do something else, and so she told them, add up the numbers between 1 and 100. And so Gauss's classmates started doing 1 plus 2 plus 3 plus 4, and it was very slow. And Gauss, a math genius, was able to find the final answer in less than 30 seconds. So the question is, how did he do it? And then how can we take this and apply it to our own math? So if you want to pause the video and think about it, go for it. There's lots of different ways that someone can approach this, but I think the way that's most straightforward and most applicable is to not add in order, but instead to think about the beginning and the end. So if I've added up all these numbers between 1 and 100, ultimately I'm going to do 1 plus 100, which is 101. And I'm going to do 2 plus 99, which is also 101. And I'm going to do 3 plus 98, which is also 101. And I'm going to end up adding 101 over and over and over again 50 times. That'll take me to the point where everything is paired up. So that's what Gauss did. Rather than adding from top to bottom, he recognized that the first number and the last number added to 101, that would happen 50 times. And then he just multiplied it out in his head to get that the sum would be 5,050. They didn't have calculators back then, so he would have done that by hand as well. Now, this actually applies to all arithmetic sequences. And a little bit more vocabulary for you. When we add up all the numbers in a sequence, we call it a series. So while we use the symbol Tn for a sequence, we use Sn to represent the sum of numbers. So for example, S10 means to add up all the terms, T1 plus T2 plus T3, all the way up to T10. S10 means to add up the first 10 terms in the pattern.